I am currently working on a roguelike dungeon crawler called Rogue Mine. And there are plenty of interesting technical challenges involved, and I have been solving them one by one. But just take a look at this. I mean, isn't that bounce just incredibly satisfying? I know what you're thinking. It's just bouncing objects, it can't be that hard. Honestly, that's exactly what I thought too. Game engines already do a lot to handle basic physics functions. So why was adding this seemingly simple bounce mechanic so frustrating? To look at how I approached this problem, we have to look at the simplest case first. In a side-scrolling platformer, gravity is simple. Objects fall downward, hit the ground, and stop. To simulate bouncing, we just invert the vertical velocity whenever the object hits the ground. To make it realistic, we reduce velocity slightly with each bounce. Very simple, right? The engine practically does all the heavy lifting. So why wasn't this the same as this? To fully understand the options we have to first consider what is available in the engine. In Godot, the engine I use, there are two modes of physics. One is a grounded mode, where floor, ceiling, and walls exist, which is ideal for platformer games like these. Second is the floating mode, where there is no concept of floor or ceiling. Think of a pool table with pool balls just rolling around, and you're looking at it from the top down, right? There is no floor or ceiling, but everything is just kind of floating around, bouncing off each other. So for top-down roguelike game like the one that I'm making, the documentation recommends using the floating mode, which makes sense because we're looking from top down. But here's a critical problem with this mode. Where exactly is the ground? The answer is everything is the ground. So if we're bouncing an object, where should it stop? Where should it start bouncing? And that is the question we need to answer. Because from top-down game, objects bouncing up and down would look just like objects moving up and down. There's no natural sense of gravity to differentiate these two behaviors. However, if you look at this or this, you can clearly tell this is a bouncing object even though it's a top-down perspective. Why does our brain effortlessly recognize this as bouncing? The secret is the concept of ground vector. Now, this is not an official term, this is a term that I came up with, but basically there's a vector that represents a ground. And as long as the objects bounce or stop on this line, our brain can simply interpret that line as where the ground is, and hence make it look like it's bouncing. So the implementation is basically just like the platformer example we use. We just draw a ground line or ground vector and have the objects shoot up relative to the vector. The object slows down as they go up until it reaches zero velocity in y direction and starts to fall down increasingly faster and faster, affected by the gravity. Once it hits or passes the ground vector, it flips its y velocity and starts to go up again. It's pretty simple. We need to choose this ground vector, but where is this ground vector? So for this example, what I've done is record where the object starts the bounce process. And from this position, I can interpolate the ground line extending out from there. And for objects that are not just going side to side, but in different angles, I simply rotate this ground line to different direction. Now, there comes a problem when the line is facing straight upwards because the entire vertical axis is the ground. So as it goes up, it's continuously touching the ground. While this ground line shows us where exactly the ground should be at some random time, it doesn't tell us exactly where the ground is given the time of the travel. So we need to actually now calculate where the ground position would be on this line given the time. Calculation is pretty simple because given the starting velocity, we can calculate how much horizontal movement we can expect. And the ground position shifts based on this time. So you can see this point of ground shifting as the time changes. So no matter what the rotation of this angle is, we can calculate where the ground position is, not just relying on the line itself, but the actual calculation of where the ground should be at a given time. And after figuring out and calculating the ground like this, the rest is just as simple as the platformer example, and we can just make it reduce energy and flip the velocity up and have it start bouncing. When you do that, you have something like this. And you can see that it bounces in all directions. And that is exactly how I solved this top-down bouncing problem. And now I can say I have the top-down bouncing object like Enter the Gungeon. Wait, hold on. Is that? No. You mean to tell me, oh my gosh, only reason I did this in the first place is because I wanted to look like Enter the Gungeon, and then Enter the Gungeon doesn't even do actual bouncing? Look at this. It doesn't even bounce. It's just spreading in 4 directions and stopping. It wasn't even that complicated. Well, I guess it's okay though, I have this. The real takeaway, I suppose, is sometimes we chase complicated solutions, getting tangled up along the way. Sure, there might have been an easier way. For example, I could have just made it hard-coded 4-direction bounce like the Gungeon does instead of doing a full-on simulation. But look at everything I learned and everything that I've discovered. Technical skills, creative problem solving, and a story to tell. So let's just embrace complexity because you never know how much you will grow or how much you will learn along the way. Now, if you had your own why did I make this more complicated than it actually needed to be moment, please share it down in the comments. And don't forget to like and subscribe and share to follow along in my game dev journey. Thanks for watching, and I'll see you next time.